Today is going to be a quicker day if you guys are okay with that. I just wasn't, I really wasn't feeling up to, and I'm muted now. Oh, no, I'm not muted. I am muted myself. So a couple things. One, I know we've got our midterm coming up. And so I kind of wanted to, kind of cover that a little bit. And if you guys have any questions to kind of answer those things, I was going to do a welding demonstration and do some oxy fuel welding. But in all honesty, I just didn't feel up with it today. I did some forklift training earlier today, and I don't know if the sun just kind of beat down on me a little bit, even though it's not that hot. And I figured I'd give you guys some time to, kind of work on studying for your midterm. That way you don't have to worry about that. But I wanted to meet with you that way if you guys had any questions, about that study guide or just kind of in general, for that midterm. That way you guys, are ready and you're prepared. I didn't want to just kind of leave you guys out to dry at all. But yeah, just trying to get everything set up and do that for the welding demonstration. Just I don't know, just didn't really feel up to it, if I'm going to be honest with you. I hope you guys are okay with that and you don't feel like I'm cheating you a little bit. I'm going to pull up where's it at here? Oh, it's going to be in this thing. Okay, let me close this down. Fall midterm. Okay, here we go. So here we can see we've got these things. I know I kind of went over this a little bit last week with you when we talked. But one of the things we want to make sure, right, that we know is these tools here. You are going to be testing on those tools. You're going to have an image. There'll be a multiple choice question. All those things are things that we've kind of used, throughout. And I've tried to make sure we demonstrate that stuff as much as possible. You can just kind of do a Google search and find those things pretty quickly. That's not that difficult. But did you guys have any questions on this midterm? Maybe some things that you want maybe a little bit more clarification on. I know sometimes the electrical side of things or the electronic, I guess the electrical side, we talk about like the DC electrode positive, DC electrode negative. Those are some things that typically, trip up kids and kind of stump them and stuff. So I don't know if you want some clarification on those types of things. But what do you guys have any questions? Have you guys looked at this? I hope you have.
Is the midterm going to be on lockdown or is it just on Canvas?
No, it's going to be on Canvas. It's going to be a multiple choice, and how it's going to work. It'll be posted by Thursday. You don't necessarily have to take it by Thursday. I will have it open for a week. Okay. You're not going to see your answers and all that kind of stuff. You'll see kind of a score. That way, when people take it, because, you might take it on Thursday, somebody might take it, on Saturday or Monday of next week. I don't really care when you take it, but because everybody's going to be taking it at different times, you won't see your answers for your questions, but you'll see your results. But it'll all be on Canvas. There's not going to be any lockdown browsers. There's not going to be any of that. We were told actually that we can't use that, or at least that's what I heard from somebody. But in either case, I don't use it anyway. The one thing that you are going to have on that midterm is you are going to have a time limit. So you're going to have an hour to complete that. So once you do start the midterm, you can't just leave that open and try to search for all the answers and all that kind of stuff. So now, that being said, I can't stop you from pulling up a PowerPoint that I put up, so that way you have it there and you can look for it. With the time limit, there should be enough time for you to answer those questions. I've never had anybody go over that time for this. There's no like number equations and stuff like that that you have to do. It's all pretty straightforward stuff. It's all stuff that we've covered in the PowerPoints and stuff. Some of the things like the tools and stuff is, that we've seen in kind of the lab, stuff like we have here. But I'm not going to stop you if you have that. I have no way of telling, but you know what? Hey, I'm not telling you to not do it. I'm not telling you to do it, but it's up to you. The best thing for you, is if you go through those PowerPoints and you look through those things and you try to find that information, okay, you'll know where it's at. And if you're looking for it, because there's a lot of information. And if you go through and you try to find this information during the test, you're gonna struggle and you're gonna spend a lot of time trying to search for this stuff. and it may be kind of difficult. But if you look at it beforehand, you look at the PowerPoints and you look at where the information is at on this study guide, that you're going to know where it's at. And if you need to reference that during the test, by all means, do it. But if you don't look at this stuff before and you try to take that test, that time limit will time out, and that's it. So that's really the only thing that you really have to worry about is that. The test will be open for a week, so you guys have, some time that you can look over this. You can feel comfortable with the information, and then whenever you want to start it, whenever you feel comfortable, just make sure you block out an hour of time where you're not going to get disturbed and nothing's going to get in the way, and then we can go from there. What other questions do you guys have?
So this is from all of our slides?
Yes. Yeah. So everything. So when you talk about like the general PowerPoint slide, when we talk about, the oxy-fuel stuff that we've done, the electricity and welding, I'm trying to think of what other PowerPoints we've kind of gone over. Maybe if I pulled up this thing. Oh, did I save that? I don't know if I saved that. If you just look through these things, if you look through Canvas, can you guys see Canvas? Can you see my Canvas page? Is it sharing that screen? Or do you still see the...
Yeah, it's sharing.
Yeah, we see it.
I don't know how this works sometimes. I don't think the introduction, we don't really have anything there. There's probably going to be some equipment questions, in there, like safety questions. I think I'd kind of put that in that syllabus. So if you go through the personal protective equipment PowerPoint, right, that stuff's going to be there. If you really look, like if you take this study guide, and there's no questions, like there's questions on the study guide, but you don't have to like answer the questions, right? They're just kind of more just kind of questions so that way, you know how to answer them. But if you look at those questions and find the answers in these things, I don't think there's anything in that one. The PowerPoints are probably the biggest thing for you to look at. And just make sure you guys know the tools, welding joints and positions, knowing those things, knowing the number classifications on the electrodes. So like a 6011, a 7018, I may throw in a different rod that we haven't used, and that's okay. But understanding, so for instance, like if it's a 4-digit number, what are the first 2 digits on a welding rod? What do they represent? Do you guys know? Do you remember? No. So on there, I'll tell you this one, tensile strength. Thank you, Caitlin. Yeah. So they measure tensile strength, and it's important to understand that it's not just tensile strength, but how much it is. And so whatever number I give you, whether it's one that we've seen before or not, if you read the numbers, it's going to tell you what the tensile strength is. And that is going to be in like, if it's a 7018 rod, it's 70,000 pounds of tensile strength. So you take that 70, add 3 zeros right to the end of it, right? So 70,000, 7018, right? Add that 3 zeros at the end. It's 70,000 pounds of tensile strength. Okay, we're not doing any other. We're not doing, any other kind of measurement. I'm trying to think of what I typically put on that test. We're not putting any kind of measure. We're not putting like bar on there. Okay. It's 70,000 pounds, right? PSI, right? Of tensile strength is what those are measuring. If it's a 6011 rod, how much tensile strength does that rod have?
Did you say 7011?
6011. If it's a 6011 rod, that's one we've used in class.
6,000 or 60,000?
It's going to be 60,000, right? So it's not going to be 6, right? So it's a 6011 rod. So the first 2 numbers, the 60, are going to represent the tensile strength. Now the difference with that, if it's a 5-digit number, the first 3 numbers are going to represent the tensile strength. So if I gave you a rod and it was a 110-18 rod, right? So we have 110, Okay, that's going to be 110,000 pounds of tensile strength. Some rods are there, but that just depends. If it's a 5-digit number, you take 3. If it's a 4-digit number, you take the first 2, and that's going to give you your tensile strength. The higher the strength, okay, the more that it's going to be able to withstand. So if we're doing like constructions, like high-rise buildings and things like that, that's where we're going to use those higher higher rods, or the higher tensile strength rods, because we need more strength in those types of things. If you're doing like stuff like bridges and stuff like that, where you're spanning over a distance, we wouldn't want to use a 6011 because it's going to be very weak. Okay, that weld's going to break, things are going to fail, and ultimately, what we try to avoid when we're building things like that is people dying. Right? If you're on a bridge and it collapses, okay, the chances of you making it out, okay, pretty slim, just like a building. And some things have a higher, requirement for that. And so that's why we see some of those rods. I'll let you guys kind of look through that PowerPoint, that welding joints and positions. It does go over the rods and stuff, so you can look at what those other ones mean. I'm not worried about the coding that's on there. There's one thing that's the coding. It's like the last digit, but it's the last 2 kind of in combination. I'm not worried about, what type of coding, because there is like a bajillion different examples. And I don't expect you to remember that, but do understand that the last digit represents the coding and the polarity. I'm just going to tell you because I'm already doing it anyway. The 3rd digit, or the second to last digit, however you want to look at that. Okay. Typically, you're going to have 3 numbers in there, and I do want you to remember these ones because there's only 3 options. It's going to be a 1, it's going to be a 2, and it's going to be a 4. Don't ask me why they skip 3. Apparently, people at the AWS, that's the American Welding Society, they don't know how to count, and they skip 3. But those ones are going to determine your position. Okay, so can I weld in a flat position? Can I weld in a horizontal? Can I weld in a vertical? And that number is going to indicate whether you can do it in all positions, whether you can only do a couple positions. That PowerPoint's going to tell you. Make sure you look at that stuff and because you will have questions based on that stuff. The electricity in the machines, that one is a pretty important one to look at. And like I said, that's where people really kind of mess up. If we are welding and we're doing something with, let's say it's a DC electrode positive. Okay. So we have our electrode holder that our rod goes into, that's hooked up to the positive. That's how we say electrode positive. Okay. The ground clamp is going to connect to negative. Do we know how power flows? Okay. Is it going to flow from negative to positive or positive to negative? Do we remember that?
Is it from positive to negative?
So electricity, okay, you guys can see this right here, right? Electricity is going to flow. Let me see, where is it at here? Did I skip it? I did skip it. I don't want to tell you the wrong thing because I could screw it up right now. Electricity flows from negative to positive. And I know I have that in here somewhere. You see how I'm even having trouble trying to find it? Oh, right here. I'm looking right at it. Electricity, okay. That's not what it is, but it's always going to flow, okay, from negative to positive. No matter what, it's flowing from negative to positive in a system. And you can see it in this picture right here. This is an example of DC electrode positive. So it's always going to flow from negative to positive. It doesn't matter how I hook up my electrodes from one to the other. If I were to swap this over and go to DC electrode negative, okay, notice how the power is still flowing. It goes from negative and it flows into positive. Okay, what piece of equipment I have and the order that those things are going in, whether it's going negative to the electrode and then to the ground clamp, or whether it's going negative to your ground clamp and then into your electrode, the power is not switching. Okay, so that's kind of an important thing because some people, they tend to mess that up and they think on a DC electrode positive, it might be flowing in this direction. On the negative, it's flowing in the same direction. We flop the way it's going, and that's not how it works. Okay, electricity is always going to flow from negative to positive. It just happens to do where in line do we connect our electrode and our ground clamp. And understand the difference between those. Like, what's the advantage of DC electrode positive? What's the disadvantage of it? Vice versa with the electrode negative. What are the advantages? What are the disadvantages? Okay, I'll let you guys kind of look that stuff up, but that's all in here. But this slide right here, or this PowerPoint. This is typically where, people kind of get screwed up because there are a lot of details. Know what an inverter machine is. We talked about, I think it's right here. I'm probably not going to test you too much on this stuff, on the AC waves and stuff like that. I know we talked about it. We'll kind of talk a little bit more about it as we get into TIG welding because it comes a little bit more imperative. If you've had me for MECAG 5, you probably have already kind of dealt with some of this stuff when we deal with motors and controls. MECAG 5, MECAG 1. If you have me right now for MECAG 1, we're going to jump into kind of motors, controls, and we'll talk a little bit more about sine waves and stuff. But I'm not going to really, I don't think I'm going to test you on that. Just understand that AC current is both DC positive and negative, okay, combined together. And AC power is what we have when you plug into your homes. But how we transfer that power, okay, is typically going to be one of two ways. An inverter machine or a transformer type. Transformer types are going to use computer circuitry to kind of modify that electrical current. Those ones are going to be cheaper, or sorry, they're going to be more expensive, but they're going to be lightweight. Okay. So you can kind of carry those things around. They're a little bit more portable. Newer machines, a lot of them are inverter types. Older machines, but we still have machines that are still being produced that are transformer types. And transformer types are going to use a transformer to basically change that power. And they also use a rectifier to change it from AC to DC. You don't need to worry about that. But understand that it's a transformer. It's going to basically step down that power or step it up, however it's hooked up. They're going to be heavy, though. Transformers are heavy. Those machines, you're not going to be moving those things around very much. We kind of, a good example is we call these tombstone welders. And there's a picture up here. You may have had old welders like this. Okay. Those ones are going to be transformer types. They're going to be heavy. They're not going to be able to move around. An inverter type would be an example like this. The ones that I've shown you that we've welded on with a shielded metal arc welding, those are inverter types. They're pretty easily. We don't move them around, but you can move them around. Good identification is a handle. I'm not going to show you a picture, but it's going to ask you questions on what it is. Transformer types are cheaper, but they're heavier. Okay. So they don't have that portability in there. And this PowerPoint goes through, what advantages those things have and what disadvantages they have right there. Okay. So look at those things. Make sure you study that stuff. Make sure you go through that. And then the other thing I kind of skipped over this, constant current machines versus constant voltage machines. When we're doing shielded metal arc welding, right, with the stick, we're using a constant current machine, meaning we set our amps up. Okay. And then we adjust those things to a certain amperage. As we're welding, our arc gap can affect that amperage slightly, but that machine wants to maintain as close as it can to the amperage that you set. So the higher you go, the more heat you're going to produce, and the more burn that you're going to get inside. More penetration you're going to get in that weld. With a constant voltage machine, we haven't really done this yet, but a MIG welder or a GMAW gas metal arc welding, that stuff is going to be a constant voltage machine. So on those machines, we're going to set the voltage up and it's going to maintain the voltage. Okay. So we're not really adjusting, that arc or that amperage on those things. There are things that we do that we can adjust that with. Okay. But we're not really messing with it. One thing about like Ohm's law, and I think, a lot of you've had me and we've talked about this, a little bit because we're starting to get an electrical in the MECAG 1 if you have it this semester. Ohm's law states that, as, voltage increases, amperage is going to decrease. They're like inversely affected by each other. And so just because we have a constant current machine doesn't mean we're not messing with the voltage as well. As we adjust one, we adjust the other. But just understand that a constant current machine, we use it for shielded metal arc welding. We use it for GTAW, that's TIG welding. And we also use it for SAW welding, that's submersed arc welding. So the underwater welding is what we use those in. That's going to be important. I'm definitely going to ask you a question on that. And then constant voltage is going to be done on GMAW, that's MIG welding, flux core arc welding, that's a kind of MIG welding. And then we also use that on submersible arc welding as well. So the underwater welding, we use it on both of those. And get out of here. Where else are we at? We did that one. The welding evaluation. That was a PowerPoint, right? I forget what's in this one. Oh, I think this is the one. Come on, pull up. Oh, that was an activity. I thought we had one. Oh, this one's oxyfuel. The oxyfuel welding PowerPoint. Okay, there's going to be quite a few, things on there. Probably some of the important things to note with oxyfuel welding. Understand the color of hoses, right? Red hoses, green hoses, what equipment that connects to. Understand how much we open valves up on each of those, the oxygen and the acetylene. Oxygen, right, we open all the way. Acetylene is a quarter to a half a turn, but no more than one full turn. On the test, when I ask you that question, it's going to be like, I'm not going to say quarter, half, one turn. I'm not going to give you those as all three of those as options. I'm going to give you probably one of those, and it's going to be the right answer, and the other ones are going to be so far off, that it's not even going to be. You should be able to do that. I don't want to trip you up because sometimes on these acetylene tanks, we got to turn them on, and we might just kind of crack it, and it lets some acetylene through. But then as you start welding or cutting, what'll happen is it'll drain what's in that line, and it's not open enough to let enough acetylene out to maintain that neutral flame as you're working. And so when you do that, you got to open that tank up a little bit more. So that's why we say quarter to half typically, but sometimes you have to open it up a little bit more. The biggest idea is just shutting it off real quick, being able to do that. Not worry about that. Oh, this one's important. Okay. Words matter. Make sure that you read carefully. Okay. The maximum PSI that we want to set an acetylene regulator up to is 15 PSI. Okay. The maximum pressure is going to be 15 PSI. The pressure that we typically, our working pressure that we've been setting up, like on our torch and stuff. Does anybody remember what pressure we've been setting on our torch? Hint, it's not 15 PSI. 5 PSI. So you may have a question that says, what's the maximum PSI that we can set an acetylene regulator to? And you may have 5 as an option. Okay. But that's not the answer. Okay. The answer, the maximum is going to be 15. Okay. That sometimes trips people up, when we ask that question, because they don't read the words carefully. You can almost have the same thing. It says, what's our working pressure set up for acetylene? And that answer should be 5. Okay. You're not going to put 15 on that. If you do that, it's going to be wrong. Okay. So just watch out for that stuff. Make sure you don't make that mistake because words do matter. Okay. And sometimes people look over it and they ask me like, well, I got this one right. And I'm like, no, you didn't, because this one word, changes that stuff. Okay. We never want to go above 15 PSI because at 30 PSI, acetylene will explode. So we don't want to get anywhere near that. That's why 15 is set as the maximum. On these regulators, do I have an example on it? I don't think I have an example of the regulator. On the regulator, this is an oxygen one, but on the acetylene one, on your hose pressure, and your hose pressure is always going to be here. Your cylinder pressure is going to be here. That's true of an acetylene tank as well. It'll have a big old red line right through here after that 15 PSI. So that's a good indication that you should not go and you should not redline it because you could cause an explosion. The one thing with all the hoses and the different things with that, not only do we talk about the colors of these things, we use red for the fuels. Typically acetylene is what we use. But the oxygen hoses have a standard thread. So if you think about like a lefty loosey, righty tighty, okay, that's true of these things. That is not true of acetylene regulators or the hoses that attach to those things. Those things are what we call left-handed threads. So you go to the left to tighten it. They do that so that way you do not mix up your acetylene and your oxygen hoses at all. You cannot mix them up because the threads are completely opposite. It will not thread on. On the acetylene stuff, let me find a picture that's got one. The tips and the cutting tips and the welding tips, those things are not left-handed threads, okay? It's only on the hoses and the regulators. I know I have an example of this stuff in here. Okay, so on here, we've got, this is a little check valve that we have here. And this one, see how we have the green? That's how we know it's for oxygen. This red right here, that's how we know it's for acetylene. But if we didn't have those colors on there, if you look at these notches that are right here, can you see those notches on this acetylene one? those notches are going to indicate that they're left-handed threads. So that's going to be for your fuel or your acetylene. The oxygen ones do not have those notches on them. So you can do a real quick visual cue. So acetylene hoses are going to be red and they're going to have notches. They're going to be left-handed threads. Oxygen is going to be like your standard right-handed threads, okay, meaning you go to the right to tighten it. They're going to have green hoses. And what was the other thing that I said? Did I miss something? Thought there was 3 things. Right-handed threads, green hoses, and no notches are going to be on there. That's what I'm missing. Okay, they're just a basically smooth thing where it's going to connect on the nut somewhere. It's going to have that stuff there. While we're on the issue of check valves, there is going to be a trick question because you guys are here and you're listening to this. You're going to be able to get this question right. Okay, this is a check valve. The way that it works, and it's the same thing if you're dealing with like water as we are dealing with like a gas. But the way this check valve works, if we have our supply gas coming in, what it's going to do is it's going to go into this valve. It's going to push open this little spring. It's going to overcome the pressure that spring is basically pushing on it. It's going to allow gas to flow past that and through the line. The way a check valve works is it prevents something from coming back. If I had more pressure this way than I did have being pressure this way, what's going to happen is that spring is going to basically force this thing closed and stuff is not going to go past this. It's one way we prevent like a flashback from occurring. Flashbacks when we have a pop, our flame is burning up inside of that torch. You're going to hear a loud whistling noise. And that means you have a flame burning up on the inside. If we don't have check valves and flashback arresters that are going to stop these things, that fire could travel back into that tank and it could explode the tank. But there's all sorts of safety guards that are in place to prevent that from happening. Check valves is one of those things. It just prevents the flow from gas in the reverse direction. So the question is, how much do we open these check valves? Like, do we go like, think about like acetylene tank or, an oxygen tank. Do we go like a quarter to half a turn? Do we do a full turn? Do we open them up all the way? How much do we open these check valves? Do you guys know? This is a trick question, by the way.
You don't?
You don't. Yeah, that's the thing. You don't. There is no valve. There's no like hand knob or anything like that you use to open these check valves up and close them down. They work independently from you having to do things. Okay. And so it is a trick question. I will put that in there. The answer is you don't open them at all, that they work independently. Okay. You don't have to worry about, opening these things up. So when you see that on the test, and you will see that on the test, don't get that wrong because you're here. Anybody else, I'm recording it. So if anybody else listens to this, they're going to get the same stuff. If they don't listen to it, I guess they're out of luck, but they should be listening to it, right? That's kind of the idea. Flashback arresters they typically have like check valves built into them, but they actually are a little bit more sensitive to the reverse flow of that gas, and they will shut it off quicker. So that way before that flame actually gets into it, there's all sorts of like different sensors and different stuff on the inside that prevents that from basically going back. It's not as simple as a check valve, but a check valve is just one way that we use that to prevent the reverse flow of the gas. I'm not worried too much about the torch body. The rods, the classifications on oxy fuel welding rods. Okay, and I know we didn't do this. Next week, I'm going to show you some of that stuff. But the numbers, typically we're going to have RG. This one's going to be a 45. That means it's 45,000 pounds of tensile strength. We don't have any flex coating or anything like that on these things, so they're a little bit more basic. A 60 is 60,000 pounds of tensile strength. And again, I don't know why AWS did this. That's the American Welding Society. But they would, the RG65 is at 105,000 PSI. I don't know why they jumped these numbers up, but there's only 3 of them you have to remember. Know that if it's a RG45, it's 45,000, right? Pretty simple. The 60 is 60,000, much like a 6011 rod. And then the 65 is 105,000. So those are kind of the 3 options. There are other ones. Those are the only ones that I'm really worried about you kind of knowing and understanding on there. Know what, sometimes you do have fluxes that we do put in there if we're welding, things like copper, silver, aluminum. We can do that with oxy fuel welding. But know what those things are. It's pretty much the same stuff. We might dip it in there. It might have a coating around the rod. The fire bricks that we actually are welding on, I think I've shown you guys those fire bricks. They're basically, heat resistant bricks that we are laying down, and it's there to help absorb some of that heat, to keep that heat up into the welding joint that we're trying to complete there. But they're not just your regular standard red bricks. Okay. They have to be fire bricks. The only place, like a common place that I have seen these fire bricks is at Lowe's. I haven't seen them at Home Depot. But if you look up fire brick, they're there. You can get them. Same things that you would put if you had like a fireplace and you want to have bricks in the fireplace. It's the same type of material there. The heat isn't going to affect that. They're going to absorb that. Has anybody ever put a flame, not like a lighter flame, but like a torch flame or something like that, on a red brick? Has anybody ever done that before? Purposely or accidentally? What happens with the brick, and the concrete's really the same way, actually. It reacts the same way that a red brick does. It will actually start to kind of eat away at that stuff. It'll pop and chips will break out either from your concrete or your red brick. So it's important that you don't just use a red brick that you had, maybe around a house for like a planter bed or something like that. If you're trying to weld, you got to make sure you get that fire brick that's going to withstand that heat. Otherwise, the brick is just going to kind of fall apart and crumble. I don't know what's going on the inside on that. I don't know exactly what's happening, but just understand that those things, are there. I'm not really worried about the sealing compounds. I don't think I'm going to test you guys on that. Okay. What's the other one? I don't think I did a PowerPoint. No, it's just a lab there. There is one. I think in this one we had this, and the welding joints and positions. And we've kind of done a lot of evaluation on welds. Make sure you understand that. The one thing I want to make sure I reiterate with you on the 6011 rod, what did I do here? Oh my gosh. Let me go forward. The 6011 rod, typically what we want to set that at is 100 on the amps. Okay. The 7018, we typically are around like 120, 125. Make sure you know those standards. That's not like set in stone. I'm going to ask that question, like, what do we set our amps up to? So I'm just telling you now, so that way, 6011 is 100, 7018 is going to be 125. I'm going to give you a range. I'm not going to give you 6011. We need to set it at 99, 100, 101, 102. I'm not going to give you those ones as options. I'm not going to be that particular, because you could theoretically do any one of those. You can adjust these things up and down. What you don't want to do is run a 6011 rod at 125 on the amps, because it's just going to burn way too hot. Things are not going to come out well. Likewise, if you turn a 7018 down, especially on like a flat position joint, if you go down to 100, it's not going to work very well. You're going to have a lot of trouble striking an arc and holding and maintaining that arc. Those rods are designed to run at different amperages, just based on those rods. So when we ask that question, we're dealing with specifically what we've done in class. So kind of what we've done, because there is some things for those of you that have welded before. And I think there's a couple people in here. If you have the diameter of the rod that we're dealing with is typically just an 1/8 of an inch rod. It's real common, real standard. As you get a smaller diameter rod, and they do have them, or they have larger diameter rods, those amperages are going to change a little bit. So if I ask a question on what amperage do we set the 718 or 6011, understand that it is what we've done, in this class, not all those other variables in there. It's very specific to what we've done in this class. And 6011 is about 100. Okay. 718 is about 125. And I'm going to give you something that's in that range, and there's going to be other options that are completely far away from that range. So as long as you remember that, you'll be good to go. Joints and positions, that's pretty standard. I don't think I need to beat, a dead horse with that stuff there. You guys can look at that stuff, but I think there's one. Maybe I'm looking at the wrong one. Maybe I need to make sure I look at this thing. So I feel like I'm missing a PowerPoint here. I do not see this PowerPoint. And if not, then that might be an issue. Maybe we haven't gone over it. Sorry, I'm just trying to find this thing, SMAW here. No, that's the one we were just looking at, right? No, did we not do this one? We did do this one, didn't we? Did I post the wrong PowerPoint up, maybe? I might have. Somebody help me out. Did we go through this PowerPoint in one of my videos?
I can't remember.
I don't recall seeing it.
I'm gonna have to look at that. I could have sworn we done this, but maybe I overlooked it. Maybe we didn't do this one. Maybe I just did the demonstration instead of it. We did talk about joints this. I'm pretty sure I did this one. Maybe I just posted the wrong one, or maybe it's not posted at all. Let me try to find this right now. That way I can help you guys out a little bit. Fire safety. I don't know. I have a 5th tab there. That's the PowerPoint one. This is how to set that stuff up. That's our lab. Okay, well.
It's in week 4. I just
Week 4? Okay. Welding joints and positions. Okay. Maybe I didn't post it. Maybe it's in the, is it in the page here? Yeah, okay. So I think what I did here, I think I posted the wrong PowerPoint up. So, you know, they kind of have similar information. So this welding joints and positions that I pulled up, the video one goes over the PowerPoint that I pulled up, and then I just posted the wrong video that dealt with that. There's some stuff. We didn't go over this one. I didn't do a video on this one. So if you watch the video, you have that. I will post right now. I'll post this in there. I'll leave this PowerPoint just so you guys have information, but we didn't do a thing on here. And this is really not what we're going to get tested on. It's really this one. And I will post that as soon as we get out of here. So this is the one that we went over in the video. It's a little bit more simplified, a little bit easier. This is the one that has your welding positions and stuff in them, right? So we kind of talked about that kind of stuff. These are the coatings. I don't want you to memorize this. I don't want you to memorize what polarity things run in. That is not something I want you to deal with. But do understand that, you know, at 1, 2, and 4, it's all positions flat, horizontal, right? We can look at those things. Yeah, I thought I was missing something, but I could have sworn we did this. Understand the electrode has a core, right? That's your rod, and then you got a flux coating on the outside. We've kind of seen some weld puzzles. The gases, this is an important one, actually. Porosity, see these little holes right here? That's porosity that comes in that weld. So could have like gases, could have nitrogen, hydrogen, you could have oxygen. Those are the 3 gases that basically pop up and cause this. These are like little like wormholes essentially in that metal, and it makes it weak, right? Because those are holes that are in there. That metal is not going to be as strong. We do different things like cleaning up the metal to prevent that. 7018 is what we consider a low hydrogen rod, which kind of prevents hydrogen from getting in there. We keep those ones in an oven so that way they don't collect moisture. And then we have that shielding flux that burns, that creates that gas cloud. And that gas cloud is what protects it from the outside air, because we have oxygen, nitrogen, hydrogen that just kind of naturally occurs in our air. And so that gas cloud, as we're melting the metal, and that's kind of the critical part, when we melt it, that's when those gases can get introduced and cause this porosity here. So that's what we're trying to avoid. That was kind of one of the main things we want to talk about. Understand, though, these 3 right here, those are the key in understanding what gases are there. It's not a carbon monoxide or carbon dioxide. Okay, it's nitrogen, oxygen, hydrogen. Those are the 3 gases we're trying to prevent from getting that porosity out there. Slag is just that stuff that's left over. You guys have seen me kind of chip that slag off. When we're doing shielded metal arc welding, that's just something we've got to do. But that helps kind of, you know, float. It kind of gets any impurities that are in that metal. 718 is a good rod for when you're welding on like rusty painted metal. We still try to clean it up, but sometimes there could be stuff, you know, micro, you know, you know, contaminants in there. Could be oil, could be different things. We don't just straight weld over, you know, painted pipe and whatnot, you know, or metal. You do have to clean it up, but sometimes in the pores in the metal, you don't see it. It's still there. That slag floats that stuff up to the top. 6011 is really great at that. 718 isn't as good, but they both still do that same thing where any impurities that are in that metal will float to the top. Ideally, you want a nice shiny metal to help make a weld good, but sometimes you can just kind of weld over. Mill scale is that stuff on metal that kind of, you know, kind of dullish, kind of gray look. When we manufacture that metal, it goes through a heat treatment process and stuff will float to the top, and those things kind of on there. You might see metal sometimes. If you've ever bent metal, stuff starts to kind of crack and break off, kind of flake off. It's a real thin layer. It's called mill scale. Some welding rods will burn through that, you know, real easy. Sometimes that stuff can cause porosity. And so if we want to do it correctly, we grind them off. A lot of times with the shield metal arc welding, we don't do that. We don't waste our time with that. We don't really get a whole lot of porosity. If you're doing TIG welding, which we're going to get into in this kind of second half of the semester, that stuff is a completely different animal. There's stuff that won't burn through. You're going to get holes. You're going to get a lot of porosity built up into those things. We've kind of talked about filling the crater, but I don't think I'm going to test you guys on that at all. All right, so I'm going to post this PowerPoint up so that way we have that. But what other questions do we have? I think we've gone through quite a bit of stuff here on this one. Do you guys have any other questions on this? No? All right. Look at these things. Like I said, the test is going to be posted on Canvas. It will be